guaranteed ones.
Yeah. Let me just turn this off also. Good. So the first part will be, I want to continue describing the theory of linear separation of manifolds. And the second part will be showing you some numerical experiments with data. All right, so I'll remind you the problem. We have Rn space. In this space, we have manifolds of some shapes, and so on. And we randomly label them, let's say plus here and minus here. And we ask under what conditions there is a linear separation, for instance here. This is W, separating the pluses from the minuses under random labeling condition for a given geometry. And for simplicity, we assume that, that they are randomly positioned and oriented in Rn. So they are d-dimension. They reside in a d-dimensional affine subspace. They are separated from the origin. We define this as the centers of them, x0, mu, which will take norm 1. And despite my drawing, the subspaces of variations, u1, mu, u2, mu, etc., up to ud mu, are all approximately orthogonal to x0, so they should be like this, and so on, and they're approximately or statistically generated independently of each other. Okay, so so first of all, I wrote down the expression for the capacity, the full expression for the separation capacity for spheres of radius r and d and dimension d. I won't write it again, but an interesting limit is a limit which will come back again and again. Well, I don't know, again, is large d limit. So large D means still n is infinity, p is infinity, alpha is finite, but now I'm taking large D. Now large D can be, in practice can be 10 or 20. Anyway, so if we do this and we take this integral expression that I showed yesterday, you find a very simple expression, which is that this is as a function of r and d. It is 1 plus r to the minus 2 divided by d. Okay. So with this expression, you can immediately answer the question, if there were spheres, the question of entanglement, entangled and disentangled, because, I'm sorry, this is an inverse of alpha. Right, so you can answer. You can see already that we discussed the case of infinite R, which is 1 over d. The entangled regime where the capacity is order 1 over d, is when R times square root of d is much larger than 1. Right, then it's simply 1 over d. So it's close to the infinite, to the subspace limit. And the unentangled is when r square root of d is smaller than 1. So there is no strict threshold. You can say r square root of d equals to 1 is kind of a crossover between the two regimes. So here the capacity is order 1, here it is order, so here alpha capacity, alpha is order 1 over d, and here alpha is order 1 because r square root of d is small, so it's 1 over r squared d, which is Can be. So already we can say this one is order 1. Okay.
Sorry?
Yeah.
Why doesn't it explode? Something is missing.
What do I mean by what?
If r squared of d is much smaller than 1, then the expression there...
Then it's 1 over r squared d.
But
This is inverse capacity. Okay?
Right.
Now,
if r squared of d is much less than 1,
yeah, it's less than 1, then the capacity is order 1. Then this, of course,
or is it order 1? It goes to...
well,
It goes to infinity.
I know, but then you need 2 corrections. Of course, we know the 2 is order 1. This won't hold anymore. We know the 2 is the bound. Right.
So this is
Okay. So there is a more refined asymptotics, and the paper elaborates on variety of regime. So you're right, we have to talk about large D, but you know, when R is very small, then of course, when R is very small, this is big, this is 1 over R square root of D, but it's limited by 2, so and et cetera, et cetera. So this is more carefully dealt with in the paper, but this is the general kind of thing. Look at R square root of D, the product of radius times square root of the dimension, and that tells you where you are. Okay, but you need to do more careful analysis to look at the details. Okay, so that's nice, but we're not interested in spheres. We're interested in some general manifolds, and the question is, what do we do there? So I described the theory, which we can do in principle by sampling T and so on. But I want to take the theory and generate an approximation from that theory. So I want to go back. I just remind you. So general manifold, and I won't repeat the entire thing. But if you remember, within the mean field, we look at a d-dimensional vector V, which is the projection of W on a given manifold, so d plus 1 dimension. And this we can write in the mean field result. We can write as a T, as a d plus 1 dimension random Gaussian, which represents the contribution from all the other manifolds, and the contribution from the same manifold that we are looking at, which is the support anchor of this manifold, which we write as lambda times S twiddle, and from this, we can generate. I wrote down the Kuhn-Tucker equations, how to for each t to compute those quantities. So I won't go beyond. I don't want to go to repeat it, but I want to use this mean field not only to compute capacity, which is just what I described yesterday, the equation for alpha m, but to actually to define a geometry of manifolds. Can I use this to the mean field to define a geometry of manifold? And the idea is that again, this I can use maybe this picture here. So if you remember, you have you're looking at the worst point on a manifold, or the convex hull of the manifold, and this gives you the anchor point, which is in the manifold dimension. It is this. So if this is the happen to be the hyperplane, so this will be the anchor point. Okay, for example, represented in this coordinates, this quantity. Good. So now what happens if I change t? So I can think about changing t, resampling this Gaussian vector as changing or resampling a different collection of manifolds from the same distribution, but just randomly position them and orientate them, and to change the labeling, whatever, okay? So then, of course, the W, the hyperplane will change. And if it will change, it may actually, for instance, be, rotated. So let's say now the hyperplane is here after the resampling of t, right? So then this is going to be our anchor point, okay? So we can look at S twiddle, the anchor point in a manifold, as a function of t, but thinking about what happened to this as we resample t. as we resample T, this point moves around. And actually, it doesn't have to be necessarily in the surface of the convex hull. It can actually also go inside. For instance, if the entire manifold is embedded, then it typically will go inside it. So it samples the points in the convex hull of the manifold. So by resampling or by sampling this Gaussian T, we define a distribution of points in the convex hull of a manifold. Let's say in the manifold, simply, okay? So then we can say, well, let's define a geometry or some statistics with this measure. So for instance, I may ask, what will be the effective radius of a manifold, or general manifold, convex hull, okay, convex manifold, because we are interested only in the convex hull. So this, I can define it the following. So remember, S twiddle, it's 1 because I'm assuming this is orthogonal to the center. So this is always 1 for all points on the manifold, so it's not interesting. But the d-dimensional S is will be the quantity of interest. So we are interested in the width, effective width or effective radius of the manifold relative to the center, right? So we're interested in that, in this d-dimensional component. Okay? So then we can define, I'm suggesting to define a manifold radius squared as S twiddle magnitude squared average over T. Now the average over T is you know, it's a complicated Disk-Kuntake procedure. You have to solve for V, you have to find the worst point, etc., as I described yesterday. But once I have this S twiddle for T, I resample T, I move around in the manifold, I can define a radius like that. You can even define something which we haven't looked closely, but I think it will be interesting. You can also define, I'll write it here, you can define a covariance matrix, CM, which will be the same story, S twiddle transpose, the whole matrix, M. And look at the spectrum, at the kind of PCA, but in this, with this measure. Okay, so this is the simple quantity, and now we can also define a manifold dimension. And the manifold dimension, what is a dimension? Dimension is how many directions this manifold is spreading, right? So it is D, it's upper bounded by D because the entire manifold is residing in D dimension. But the effective dimension may actually be very small. If there is only one actually long direction where things are changing, then we expect that the effective dimension may be rather small. Okay, now we know it already from the PCA kind of thing, but now we'll do the same thing, but with this measure. So the effective dimension turns out to be this little s dot the unit vector of the Gaussian T. So again, T itself is the dimension. T0 is the projection of the weight vector on the center, and little t is the d-dimensional projection of T in the subspace itself. So we are looking at this and squaring it and average over, I'm sorry, it's opposite. We absolute value on the S and average over T again. So looking at the projection of the vectors on the random Gaussian T, which represent the noise in the as we said in the weight vector. So this is well-defined quantities, and now we can ask, okay, so does it help us or not? So it turns out, I'm not going to prove it, that you can also ask now what happens with large D. Yeah.
Is that also close to trace of CM?
That what?
Is DM also close to trace of CM?
No, it's not. You have this is a unit vector. You have to divide by, it's not a simple relation to that. Okay, it's not. T enters here. Okay, we can discuss later on. What enters here, the direction, you have to make sure you have to make sure that you sample all possible directions. So this is what this Gaussian is doing. And there is this is an extension of a well-known convex hole geometry measure, which is called Gaussian width of convex holes. This is kind of an extension of those. In their case, there is no V. V equals T. So it's simpler, okay? But again, I don't want to go into it. You can read it in the paper. Okay, now you can ask what happens for the capacity. Does it help us? What happens to capacity when D is large? And more carefully, I would say when dm is large. And it turns out that the capacity in this case, and again, as Nati already mentioned, you have to be careful how R, but in general, kind of alpha m in this case, is basically like alpha spheres with Rm and dm. So in other words, you just replace the geometry of the complicated geometry of the manifold by just equivalent spheres. And furthermore, in a wide parameter regime, you can actually use this. And you say that the capacity is simply 1 plus Rm inverse radius square times dm, divided by dm. This is the inverse capacity. The larger the d is, like here, the lower the capacity, makes sense. The larger the radius, the lower the capacity. And again, here again, as I said before, when Rm is very small, then of course it's bounded by that. So you have to assume Rm is, this is true, if you want to be more careful, this is true here when R, both of them, or write it here, when Rm square root dm so dm is large, but this is not, the product is not, is not too small. Otherwise, you're going to the point regime. Okay, but in any case, this gives a lot of intuition now what's going on. So for the capacity, and we find numerically, empirically, that high dimension is very relevant to the data, to kind of real data. So that this is, this is not bad approximation. Of course, you can do better work if you use the full thing, the full capacity expression, as I said, by sampling T and so on. But this, what you're doing here is the following. You're using the Kuhn-Tucker theory to compute the effective radius and dimension, okay? But once you have these quantities, these statistics, you can just guess what classification capacity is. So there is a very tight, in this large D regime, there is a very tight relation between a simple geometric measure, simple, I mean radius and dimension, and capacity, but of course the radius and dimension themselves are non-trivial, are not simple. Okay. And again, you can see here when Rm is large, then it's 1 over dm, and when Rm is small, then it's order 1, and so on and so forth. Small, in this regime. So you get the same story here, and again you get the same story that when Rm square root dm are large, then alpha m is order 1 over dm, and Rm square root of dm is much larger than 1, sorry, and here it is order 1, then alpha m is order 1. Okay, so if you want, again, in general manifold, the separation, so to speak, between entangled and unentangled is not a clear cut. There is no threshold, but this is kind of the crossover regime between them. Okay, so now, but I just want to add that this is I think an interesting geometric measures coming out of the mean field, but it is a collective measure. It's not a simple geometry in the following sense. The Rm and dm that I described here, I said, well, look at the manifold and see how the points move in the manifold as you resample T, okay? However, the resampling T, remember, to solve this, It will depend, for instance, on alpha, on how many manifolds you have. Or it will depend on, conversely, on the margin that you demand. For given alpha, the margin that you demand, and so on. So it's a collective geometry. It's something like in physics you say the electron has a mass, a bare mass. Sometimes they think about it as zero, or sometimes they take it infinite, depending in the field theoretical construct. But then they say the real mass is a dressed mass, is a normalized mass, is a collective. It's the electron inertia, but dressed by the interaction with the environment. It's something like this. This is the dressed geometry. This really depends on the geometry. For given statistics and number of manifolds, this is well defined, but okay, so you have to be careful about that. And that has many fascinating properties, which maybe I'll mention one of them, is the following. So the separation between these regimes, unentangled and entangled, has an interesting also effect on the geometry. What happens is in this regime, this effective mass is effective properties are turn out to be single manifold properties, but not in this regime. So here's the exercise that we can do. Let's suppose we have these manifolds and we shrink them with some scalar r. Remember, I introduced it yesterday. So you take it and you shrink it. You take this and you shrink it, and so on. Or else you expand it. So you introduce this scalar r, okay? Now, if this was a true geometry in the sense of mathematical, in the sense of Euclid, then, of course, we know what happens. When r changes, radius will just scale with r, and dimension will not change, right? This is true in this regime. In this regime, if I introduce this global scaling, that's what will happen. dm will be independent of this little r, and Rm will scale linearly with little r. In this regime, this is the entangled regime. It's tight. Every manifold is. So when you shrink r, there is more space. When you increase r, there is less room. So then these quantities, dm, for instance, it becomes a function of r, which is. So let's imagine we do ellipsoid with some spectrum, and then you ask what is the effective dimension as a function of this little r. So you fix the geometry of this. So you just have ellipsoids here. You fix the geometry, and now you say what happens if I shrink the ellipsoids with the scalar r. So this is the dimension, and this is the radius for ellipsoid. So in the dimension, depending of course on the spectra of radii in the ellipsoid, for small r, actually it can be. This is the actual dimension. This is a small r. It can actually be very small, not zero, but very small, 1 or 2. Okay. And however, for as r increases, it crosses over to d. So if d is large, there is a crossover regime. When small r, the effective dimension of this is small, much smaller. It's order 1, even if d is large, but it can be. But here it. So as r increases, and there is an intuition about it. As you scale r's, the w has to attend to all possible dimensions of the manifolds, even if there are little less variability there, because it has to find a room to optimize the hyperplane. So it has to access all possible dimensions of the manifold. So you just see it, as long as the variability is not zero there, you just explore the full dimension. But when r is small, you just have to attend to the longest directions. So d can be small. And rm, similarly, if you look at rm over r, so here it's linear. So the ratio is basically stay fixed. And then when you go to this entangled regime, this is sublinear. Rm is suppressed. It doesn't increase linearly, but sublinearly. Okay? So this is the crossover which I'm talking about between unentangled and entangled. So it does come up as how the effective geometry changes as you make the problem harder and harder. Okay, so there are a lot more data and results in the papers, and I'll stop here. And I want to switch gear before I'm talking about numerics, to switch gears to another problem, again with manifolds. And this is generalization problem. So until now, I just talk about, I have data. The data can be infinite number of points, so full spheres or ellipsoids or whatever, or I can have some empirical finite number of points organized in manifolds, and this is the result, okay? Now I'm asking generalization question. So suppose the real manifold are large, maybe even infinite, like infinite number of points, like spheres or ellipsoids, etc. But I have subsamples of them. Okay? So the same manifolds that I described, that now the manifolds are an underlying model of the data, and I see only subsamples of them. I find them the linear classifier on the training data, and I'm asking what will be the probability of error for a test data which is sampled from this underlying manifold. Okay, so this is the generalization. So training on some sample on m points per manifold, and test on new test point from the manifolds, from the underlying manifold. Now, this is hard problem for many reasons, but one practical reason, I discussed it yesterday with some of the students, is that what's nice about the training problem is that it doesn't really, the results so far don't really depend on how you precisely you measure the points on the manifold, as long as the measure is non-zero. So suppose I'm separating spheres, but the actual manifolds, are not. It so happens that not uniformly sampled. It doesn't matter because to classify it doesn't care about the actual distribution or measure on the manifold, as long as the measure is non-zero, okay, or the convex hull and so on. Okay, but generalization is different because now I have, well, in principle, I have to ask, well, this is the probability. The probability will depend to some degree on how I sample the actual manifold. So typically, sampling the actual manifold is not sampling its convex hull. It's sampling the actual manifold with some distribution. So it's hard a problem in the sense you have now to introduce a model of the actual distribution of the manifold. It will not affect your training part, but it will affect how you measure the generalization error. So we can assume uniform distribution on spheres and do the work, etc. So that's one point. The other point is, the measure of test points. The other issue is that it depends on the geometry, of course, but also on how many of them. So if I have m points per manifold, but p is large or alpha is large, then the probability of error will be, of course, will be larger. You can think about it from the perspective of margin. If the margin is small, then the error will be large. So I have to specify also that alpha, let's say, how many subsampled manifolds I'm treating during training. Okay, so it's a rich problem, but I want to make my life simpler, and I say so depends on the measure, but also depends on alpha. Depends also on alpha, the answer, the probability of error. But I want to focus on the dependence let me edit here, on the dependence on the geometry. So it will depend also, of course, on the geometry of the manifold. Okay? And I'm asking how this generalization error is dependent on geometry, because I like geometry. I like to think in terms of geometry. Okay, so I want to make my life easy here. So I want to say, let's take the simplest case. Instead of, some things, thinking about alpha and near capacity and so on, I take the simplest case, 2 manifolds. Okay, so I subsample 2 manifolds. I find the linear separator, and I'm asking what will be the probability of a new point. And since it's late and after lunch and so on, and everybody's tired, let's do our life even simpler. Just have 2 spheres, d-dimensional spheres, subsample them, and ask what is the probability of a new point to be misclassified. Okay? Good. I can make my life even simpler. Just 1 sample per manifold, per sphere. So now this is a task that all of you can do, right? So let's just do it. Okay? 2 spheres. Alpha is 1 or is 2 over p or 2 over n if you want. Okay, so I have 2 spheres. I'm writing it here because I'm going to make my life even simpler than that. 2 spheres, d-dimension, the same radius. In n dimension, again, I'm drawing it in the wrong way, but they are again orthogonal. The same story. They are really disc like that, right? Orthogonal. Anyway, so now I'm drawing it in the wrong way, but sorry for that. Now you have a point from here and a point from here. What is the probability of error? Okay, so what will be, first of all, what do I do if I have just 2 points? I point here and point here. Let's say from the surface for simplicity, but it doesn't matter. Okay, so these are my 2 examples. And I am asking about, I want to train it, okay? So I don't have any more data. This is the only point. So obviously what I'll do, I'll draw the line between the points. I'll have a separator W in the middle of it, and this will be my classifier. There is nothing else that I can do without more information than just 2 points, right? This is point 1. This is many example on sphere 1, example on sphere 2. I connect them. I'm sorry, this is the plane, not W. W will be here. This is W, this is the plane, halfway between the 2 points. And now I'm asking a simple question. Now, giving a new point, what is the probability that a new point, let's say here, will have negative projection on W? That's the question. That will be an error. Even that is hard for doing it right after lunch. So here's a simpler problem. I have a sphere, 1 sphere, and I have point or few points, and I want to find a separator from the origin. Basically, it's the same problem, right? If they are symmetric like this, then finding separator between those is like finding a separator. So it's just a simple case. 1 example, I have 1 point from a sphere, and then I'm asking, okay, what do I do? Separating it from the origin. So this is W. I draw a plane. Okay, you can see that the error will be perfect. The error will be 0. Okay, but what happens if the sphere is bigger? Okay, so let's imagine. Well, I have this sphere here, separating from the origin, and maybe I have a point, a point here. So this is W, and now, the best hyperplane will be here. Now I start to have error. Okay. So so let's calculate this. It's relatively simple. I have 1 point from a sphere, and I'll use my notation x equal to x0 plus r times u. You can always choose u1 one of the coordinates of the sphere to be the point that you sample. So let's write it U1. Okay? And now so W will be this. So now I'm sampling a new point on the sphere. So the new point will be Y, which will be again X0 plus R times sum over J, Uj, Sj, J goes from 1 to N. Okay, and now I'm asking what is the dot product. The dot product will be, assuming the U's are orthogonal to X0, then X dot Y, Y dot X, which is the same as Y dot W, right, will be 1 coming from the center, plus here there will be R square, times, again, X0 and U's are orthogonal, so only the U1 will enter, so it will be U1, I'm sorry, not U1, U1 square is 1, times S1. S1 is the coordinate, is the projection of the new point on the sphere on U1, on the direction of, so this is the center, this is U1 now. Okay, so this is the result. Okay, now what can we say about S1? S1 is, we know that S1 is uniformly distributed, so its angle, its unit vector. S is unit vector, right? Remember, S is unit vector, and then and it's uniformly spread. So each component of S will be D is large, will be approximately Gaussian, with the variance 1 over D. So each component of S will be variance 1 over D. Because the sum of them is 1, and there are D of them. So this is like Gaussian noise with variance 1 over D, and the error would be when this total thing is negative. So, if I introduce the H function is, the tail of a Gaussian. Let me write it down. H of X is defined as D of U from X to infinity, where D is the Gaussian measure. Then what I'll get here, that the error, probability of error, is H times, so that's 1 over D, so it is square root of D over R to the 4. Right. Okay, the way I want to write it is slightly different, because I want to generalize it to a more general case. I want to say the following. What is this R? R is normalized to the distance of the sphere from the origin, which I decided to call it 1. So instead of that, I can write this as, in general, as S signal to noise, SNR, where the SNR is, I'm writing it this way, it is R squared, which is 1 over R squared, which is delta X0 from the origin, normalized by the radius, divided then by square root of inverse dimension. And you'll see later on why this is a nice way to write it, okay? So look at this, it's interesting. When R is large, yes, then it's like the distance. So delta X0 is the distance, is the squared distance from the origin of the center, normalized by the total variance, which is R squared. So it's distance squared normalized by R squared. So this is, instead of writing, in terms of R, I'm writing in terms of delta X0. The displacement from the origin, of the center from the origin, normalized by the radius of the sphere. And then a dimension. So that's natural to think about the larger R, the smaller the normalized distance, the larger the error is. It's clear. But look, the larger the dimension is, the smaller the error. Right? H looks like H of SNR. When SNR is 0, the H is 0.5 random. When SNR is large, it falls exponentially to 0. When D is large, the SNR increases. Now, this is surprising. Until now, we said large D is bad. Of course, this is intuition. But now, large D is good. For a given radius, if the dimension for a given total radius and distance from the origin, if the dimension of the sphere that I want to be able to generalize well from one example, the bigger the dimension is, the better I am. It's strange, okay? There is a simple intuition for that. Okay, but this will be this will be dinner talk, but that's very interesting. Okay, so, but before I go on, I want to say that's not exactly true. And again, I'm hand waving because the details are more complex. Because you can see here, when R is small, like here, then the error is, then one example is enough, right? Because no matter where the example is, all points on the manifold will be classified because the separator will have perfect on the R. And so you can see that R equals to 1 is the case because the worst case is that you sample a point here and the new point is here, then it's 1 minus R squared and basically the error is 0. So the true answer, the correct answer here, will be R to the 4 minus 1. And again, it's more complicated, the expressions, but we are going to assume that we are far away from this regime. But that's an important point. For manifolds which are bounded, like we assume, like spheres, below some radius, it's true for a general manifold, below some radius, you can generalize perfectly from one point. Okay? It will be 0 error. But here I'm saying, so this is because S1 is not really Gaussian. It's a unit vector uniformly on the sphere. But I'm saying I'm not in this regime. But when you fit it to data, you have to be careful. So I'm assuming that we are not in this regime, so R is substantially bigger than 1, such that we can just approximate it by this way. So again, you can find in the papers more details. Okay, so that's exercise number 1. Now you can do the same exercise as separating an ellipsoid from the origin. Okay? And it will not be hopefully surprising to you. So this is spheres. So ellipsoid from the origin, and again orthogonal to the direction, to the distance vector, it will be similar. Epsilon g will be again h of the SNR. And now the SNR had the same structure, will be delta x0, normalized distance from the origin, where r square, in the case of ellipsoid, is simply sum over I from 1 to d of Ri, the total variance. And then here there will be the square root of effective dimension of ellipsoid, minus 1. Again, when the effective dimension is large, then this is then you are better off. But what is the dimension of the ellipsoid? It turns out that the effective dimension on the ellipsoid is given by sum over I from 1 to d of Ri squared, everything squared, divided by sum over I from 1 to the d of Ri to the 4. And this is well-known measure of dimension. This is known as a participation ratio. Right? Because it tells you how each mode in the kind of PCA, how each mode, how much it contributes. So if Ri's are concentrated on one mode, then this is just this will just be 1 divided by 1. So the effective dimension will be 1. The effective dimension And if Ri are uniformly spread, so then this will be d squared over d, then it will be d. So it's interpolate between the two regimes. Okay? Okay. So the bottom line is two things. First of all, the orthogonal to the classification problem, the larger the dimension is, the better off you are, in this sense. And secondly, the effective geometry which enters is simpler. It's not the kind of a mean field dressed. It's very simple. It's just the good old participation. The radius is the sum over this, and the dimension, the participation ratio. And now this is not a coincidence. It's because this problem, from the training perspective, is extremely simple. You don't have this near capacity. You just have one point to classify. So obviously, this is a much dilute environment to worry about all this collective effect and so on and so forth. Okay, so this is here. Now I'll write to you the general answer. The general answer will be general manifolds separating a pair of manifolds, not from the origin, but from each other. And again, here, it turns out, just a moment, it turns out that in large D, you can think about this general manifold as ellipsoids, and just write down something like that. But yeah.
Just to better understand this fact that increasing the dimension, we are better with generalization. Is it because, I don't know, the fraction of volume which is not classified correctly by the classifier becomes smaller and smaller, increasing the dimension? I don't know, in this two-dimensional picture, I have just one small piece of...
But another way of thinking about it is to say, well, I have a random point, the test point, random point, okay, and ask what is the projection of this random point on a given direction on this, okay? And the answer is it will be Gaussian around 0, but the width of it will be 1 over square root of d. Right? So the point is, what we care, so we really care about something like that, but we really care along this line. So, right? So in other words, okay, I can, yeah, but you understand my point. We really care that it won't leak to the negative part. But if it is centered around 0, okay, then we are better off. So the centering of the project, so you have a given radius r, and you ask as a function of dimension, what is the distribution of a projection of points on the sphere on a given fixed direction? Let's say on the x-axis, okay? And the answer is it's effectively Gaussian with the width 1 over square root of d. So the larger the d is, the smaller the scatter of the projection, and therefore the less likely it will be going to negative, to cross the line. All right, so let me just write down, quote here, the final expression that we have for SNR. So in general, and I'll say what is in general. General manifold, pair of manifold. We just approximate them, again, high dimension, approximate them as two ellipsoids. Not necessarily with the same geometry. And I'm also assuming I have m training points, not one. M samples per manifold. Per manifold. Okay, so what we get is the SNR. Again, it's the same expression with H, but the SNR now is more general quantity. Now, because it's not from the origin but 2, there is a factor of 1/2, but it's not important. There is the signal, again, the distance now not from the origin but from the centers. This is now the distance between the centers of the manifold. So I have one here, another one here, and I'm separating between them. So I'm looking at the distance between the two centers. So this is delta x0. And now down here, okay, so I have to, of course, because I'm not assuming that they are the same geometry, I'll say the probability of error for a test point on one of the manifold. It's not necessarily the same. So the error of a test point on one of the manifolds, let's say A. So this will be a function of M, and it has this SNR, which is a function of M, the number of sample points, but for one of the manifolds. And you see how the asymmetry will enter. So this will be now this inverse effective dimension enters here, divided by the number of points M, plus the dot product between the displacement vector delta x0 and the subspace U of the manifold, the other manifold, M. So it's a subspace. You have to sum over all U's of B's and collect this is the overlap between subspace of manifold B on the displacement vector on the signal direction, and again divided by M. It's all in the noise term, and then delta x0 dotted with UA. Again, this is the matrix of all the U's of manifold A squared. And then finally, there is a bias term on top of here, which is RB squared RA minus 2 minus 1 divided by M. And by the way, this work is done with our friend Ben Sorcher. And you can ask all the details from him. And Surya, of course, Surya Ganguly. Okay? So this is a more general expression separating between two manifolds on the basis of M samples per manifold. And now the geometry is more general. There is the delta x0 is not necessarily orthogonal to the U's, so there are these overlaps. This is a subspace signal overlap of the UA and the UB, and there may be we call this a bias term because this is the radius. If the radius is different, then this can be either positive or negative. So you can even make worse than chance error if there is a big discrepancy between the radii of the two manifolds. Okay. And finally, I want you to pay attention to the fact that how M enters. M is the number of sample point on the basis on which I'm doing the training, and you can see there is M here, and M here, and M here. So when M is large, this drops, this drops, this drops, but the SNR is still finite because you have this term here. So that's strange. I have infinite number of points. Why my classifier doesn't give me a perfect solution? And the answer is, which I didn't tell you, and I want to tell you now, is how do I do the classification when you have M points? Right? So now I have 10 points per manifold, and I'm training a classifier to separate them, and I measure the error. Well, if I have 2 points, then the only thing which I can do is draw a vector and take my W to be along this direction. But if I have M points, I can do many things. I can do sophisticated things. I can do nearest neighbor classifier and so on, or max margin classifier on them. So what is this expression about when I say M training point? So now I'm saying what this is a result of a primitive and very simple protocol, which I'll say the following. We have M points, so I'm just drawing the centroid of these M points, let's call it X hat of A. I'm just averaging over, I'm just computing the center of mass of these M points, X, these are my samples from manifold A. And just computing the centroids for this, and similarly I do it for B, and then I'm back into 2 points. Okay? So it's a very simple-minded algorithm. Take your examples, average them, you get an effective center, kind of an estimated center of the two center. Do it for the other one and draw W between them. This is not an optimal way to do it when you have m points. The very least you can say, let's do max margin classifier and don't average them, okay? Or nearest neighbor classifier and so on and so forth. In terms of cognitive science or in terms of philosophy, doing this is the analogous of prototype learning. Right? It's a famous question, millennia old questions of how humans learn new concepts. You see examples. At what time you say, well, these are new concepts. I can separate between concept one and concept two on the basis of a few examples. And prototype learning says, well, as you see examples, you average them or you pick some typical one, but you keep only one. You don't store all the examples. You just keep one and update it. You keep another one, update it. So these are the prototypes. And your discriminating classifier will be based on that. So it's called prototype learning. And that's what we are doing here. This is the result of an algorithm prototype learning. Another one is exemplar learning. So you actually keep the examples, and when a new image comes, you're saying which one is close to which one. So it's basically similar to a nearest neighbor. So exemplar learning. Learning, yeah. So this is this will be an analog of nearest neighbor classifier. Okay, but this expression is for this one, and you can see here, as long as m is small, it's fine. But when m is large, then obviously you can do better by this more sophisticated classification because you will converge to 0. All right. So all this story here, if it's wasn't clear to you up till now, it's basically the context of few-shot learning. Right? We have two new concepts, many in the language of manifold. You see a few examples from the two concepts, and learning them in this context means being able to discriminate between them if a new image or if a new signal is coming. Okay? So that's a few-shot learning. And as I said, from the cognitive science perspective, there are at least these two paradigms, but there is, of course, a lot of empirical data that humans do this and combination of this, and it's complicated stories and still arguing about it. But we are just asking the question of what type of geometry enters into the representation of manifolds, of the neural representation of manifolds, on which this prototype learning is done. Okay, so by now I want to switch to the PowerPoint, not the PowerPoint, the presentation. Where is my friend? Can help me? Yeah, okay. Okay, so we have gone through the theory. So no, we're not going to discuss this. And so what I want to discuss is some empirical data. By empirical, I mean using the measures that are derived from the theory to assess the representations of objects either in artificial deep convolutional networks or in some data that available in the visual system. And I want to do it from the perspective of two classes of computations. One class of computation is high density, high capacity separation of manifolds, and another class is this rapid learning of objects. Okay. We've done this, we've done this. We've done this, Jan LeCun slides. Okay, we've done this. Okay, we've done this. Okay, we've done this. I want to repeat it. I want to go to the data. Okay, so this is okay. Well, maybe I have an example. No, too bad. Maybe I have an example of just a moment. I want to show an example of. Maybe I have it here. No. Where is it? Here. Here. Okay, I want to show you a demonstration of the anchor point. So and how they change. So suppose I look at the manifold, ImageNet manifold of vase, and I have other manifolds, and I'm separating by the maximal separating hyperplane, and I'm asking what is the anchor point of this manifold vase. So the centroids, so to speak, a typical value, a typical vector will be a kind of a standard. This is a cabbage head. This is a vase. But if you look at the anchor points, because it so happens that it is close to the cabbage manifold, it looks like a vase, but somehow similar to a cabbage-looking vase. Now you do the same vase, but you reorient the other manifolds. So now it may happen that the anchor point is actually close to the other side to a birdhouse, and then the anchor point will actually look like a vase in this case, with a picture of a bird on it. So it's somewhat similar to adversarial examples. Okay, these are extremal points which are kind of overfit due to the nearest manifolds. All right. Okay, so this is ImageNet. You all know about it. Okay, so yeah. So let me just briefly give you examples of how we do what we do. So this is an example of taking Alexnet and using manifold simply as PowerPoint as a point cloud. So we take a category and we sample either all the points or subsample of the points, depending what are our computational resources, and we fix this and we compute by theory or by simulations the capacity of classifying randomly labeled manifolds, classifying them, linearly classify them. And we do it along the pre-trained network. We're not training the network. We're training the classifier, the linear classifier on top of each one of the layers of the manifold. Now, what's nice about this measure is that you don't really have to take the full, I don't know, million or whatever, or 70 or 200,000 neurons in each one of these layers. Because of the extensivity in the thermodynamic limit, the capacity is P over N. So you can subsample. You can say, I take only 1,000 neurons randomly sampled across the layers. Or in each layer, I just take 1,000 neurons. So the dimensionality N is 1,000, is fixed. Okay? You can either subsample the neurons, or you can do linear random projection and subsample the projection. The difference is not substantial. So this way, you can. It's much easier to handle the problem is by thinking about P over N. So what you actually measure is if you want, in terms of information, is the amount of decodable information about object identity per neuron in each one of the layers by this measure. Okay, so here's an example of Alexnet. So this is the different stages. The feature layer is the last one, and this is alpha C. So you see here 3 curves. This is the actual curve of the capacitive pre-trained network. It goes from kind of order of magnitude increase, and interestingly, there are two baselines. One baseline is before learning. So the question is, maybe the architecture itself is doing this. So what happens if we just initialize the network with random weights, and then you measure this on the random initialization, and you see that there is slight improvement, but not much, but basically stays at the same as the pixel layer. Now, what happens if you are randomly labeled? You take all your data, but randomly label them, as I discussed yesterday, so 2 over m. So, depending what m was here, this is the line, okay? So you randomly label, you basically stay at the base. So what you see here is interesting, that if you look at the actual curve, you start from the pixel layer, it's only slightly above randomly labeled. So you ask, what's going on here? So I have data on objects, and I am separating them eventually nicely here. But how much information is there about object identity in the pixel layer? Well, this is the answer, this much. If it was completely random, then there was no way to resurrect it afterwards. So this amount of information about object identity, residual structural correlations in the pixel layer is what's being used in the network to amplify it and to generate this higher capacity. Okay? And we have done a more careful work and to actually compute this. It turns out, as I told you, in a random case, it should be 2 over m. If it was truly random, if the input was random, then the capacity will be 2 over m. It turns out that it is 2.1 plus 1.04 or something ridiculous number like that as the 0.01. But this one and this one are what is saving the story. These are the deviation, the small deviations of the information about object identity that resides at the input layer. And this is what is being amplified by the network. Yeah.
So this alpha is about linear separability.
About what?
It's about linear separability.
Yeah, it's all about linear separability.
So
yeah.
Why, if you have something which is at the chance level, you can't amplify afterwards?
Well, here, if you ask about nonlinear decoding, well, this is what nonlinear decoding is doing, starting from here and coming to here. This is the nonlinear decoder. The entire network is the nonlinear decoder.
I'm sorry, if I understood, you said that difference from chance is important at
Yeah.
the pixel
Yeah,
level.
yeah.
Why, if it's at chance level, it won't work?
Could be. I mean, this is one measure. Okay. I'm not sure I know what is the question. This is a chance level from the perspective of linear decoding. It's not a chance level. These are the deviations from a chance level from the perspective of linear decoding. If you ask me what is deviation from the perspective of nonlinear decoding, 0.1. This is the nonlinear decoding of the pixel layer. So I don't know what to say, right? Right? Obviously, the information about object identity, even after 1,000 layers, is all coming from the input layer. So the answer is nonlinear decoding, information theoretic. This is it. No, it's a bound on that. But the whole story about the deep network and reformatting the data is that the problem is not that there is no information about it. The problem is about what is the format of the representation is to enable decoding of it. Okay? The information here is using the information in the inputs. If you use this measure, it's huge, right? So this is not about information in the sense of information theory. It's about how much information can be extracted from a linear decoding. Okay, and similarly the radius and the radius and dimension. Okay, so I have to run quickly. Alexnet. This is now a larger network. We wanted to see what's going on. It's kind of interesting. You take ResNet 152. You see, and this is in many layers in many examples that we studied. you see this effect. This is pre-trained network. There is a gradual increase, incremental increase in capacity as you go through the layer. And then the last stages of convolution, downsampling, and fully connected, you see the increase in capacity. So it's interesting. To me, it does not mean that you don't need this. It just means that these stages are important, perhaps, for generating this eventual increase in capacity. But the increase in capacity actually emerges only in the last stages. And you can see the same with the radius and the same with dimension. And by the way, this sudden decreases coincide with downsampling. Okay. Now time is running short. So in the paper we have all the analyses that that are important. But let me just give you one more point. I didn't discuss correlations, but the manifold, the centers of the manifolds, are actually correlated. I assume that all the manifolds are uncorrelated. So we looked at the correlation of the centers, Pearson correlation of the centers. And interestingly, the correlations are relatively high, the pixel layer, and drop considerably, almost to random, not random, but at larger. And our analysis of capacity shows that the capacity, in addition to the radius and dimension, the capacity is also benefiting from reduction of correlation. So the old idea of decorrelation of signals, which we love in the in early sensory processing theories, appears also here in high-level theories. But I want to actually summarize this, that if you ask what happens, how networks, what happened to the geometry of the manifolds, is a very significant reduction in the radii, in the effective radii, and very substantial reduction in the dimension of them. So disentanglement means that the effective radii and dimension are shrunk in the last layers of the manifold. Now, what about data, neural data? So there's a lot of neural data, not question about them, but I want to show an example which I like, unpublished yet, but I like this example. It's maybe anecdotal. We have to have more data and more statistics, but anyway, I'll show it. So this is the results from Freiwald and Tsao, an old paper in Science, where they looked at the monkey IT cortex and identified patches in the IT cortex, which are selective faces, not objects, but faces. And they did it on the basis of showing the monkey something like 28 faces, and each face with some 8 poses, okay, as you can see here. So this is the images, okay? And the monkey was, I think, viewing those, and then they measured the neural responses. So we took the data for each one of the images. We have about 200 neurons responding to them. So we can actually construct manifold. It's not a very impressive manifold. It's manifold where 8 points per manifold. But still, we ask what happens to these manifolds that correspond to the selectivity in IT cortex. Okay? So let's forget about this for the moment. So here's what we did. We took the same images of faces and passed it through VGG face. So this is a deep convolutional network, but specialized for faces. And this is this line here, capacity, as a function of the layers. And the feature layer is an increase here. The feature layer gives capacity, which is this value here. Now, it turns out that this is the capacity that we get when we measure the IT cortex. There's the neural responses. Okay? Now, the point is, there is no parameter here. It's not a fit. We don't have any parameter to fit, right? We just take the neural data, we measure the capacity as the procedure I mentioned, the linear classification of the data of these manifolds, and we just measure apply the same measure to deep convolutional networks, specialized for faces, and extremely close. If we do this for deep convolutional networks that are specialized for objects, not faces, you see a lower capacity for the same images. So it's not that everything goes. So really you need a convolutional network that is specialized for faces to reach the capacity of IT cortex. The differences are small because the data is relatively poor, but nevertheless, I think this is very suggestive, because what I'm impressed about it is that there is no parameter to fit. That's what we get without any parameter fit. This is 3 stages in the IT cortex that are specialized for faces, and they have an anatomical argument why there is a hierarchy among them, and that's consistent with our capacity measure, that there is a well-defined order. So these are more selected to faces, this is less, and this is less selected to faces. All right, so the last 10 minutes or so, I want to jump to something else, which is the rapid learning of new objects, which is this few-shot learning. There's an archive paper on that. But I want to, okay, I can skip the demo because you all know what we are doing here. We are showing, we'll take pre-trained networks on ImageNet, and we sample points from held out image objects, classes. So ImageNet is 1,000 classes. There are more thousands of classes which are not used for training and not for validation, held out classes. So we take 2 images from 2 categories, okay? So these are 2 images. And then we ask what is a new point, whether this is, whether the new point belongs to Numbat on Quat. And I hope this is, I think it's Quati, right? Ben, what is the answer?
Are we so good at this?
Yeah, I'm not so good at it. Anyway, so you send them, and this will be 4-shot learning. Again, the same task where you show 4 examples, and you ask does this fit to this, or does this fit to this? Okay, so this is the few-shot learning task, and so I can skip all the thing because I already explained to you what is prototype learning. We take each layer, but in particular we take the feature layer of the brain, or the feature layer of the deep convolutional networks. We take our samples and we average them. We take our samples and average them. We just draw a line, dissecting it in the middle, and this is our prototype learning, and we ask what is the error for a new point. I described it, okay. So first of all, so this is the theory. Okay, first of all, here's the result, which was surprising to me. I'm not saying it's surprising to machine learning, but to me, that the error is, the error is extremely small. The accuracy, the average accuracy on many of these held out categories is extremely, it's 2% error, okay? For untrained, if you don't take the pre-trained network, you just took the untrained and you do this, you get almost chance, okay? The pixel layer is slightly better, but it's again, much worse. So this is now the distribution. It's not, this is few-shot accuracy. That's the distribution in the untrained. This is distribution in pixel layer, and this is the distribution in the feature layer. So I think it's very impressive, and now it's really asking the question, begging the question, what's going on here? The network have been trained with 1,000 specific categories, and now you show 2 different categories. The network that not only didn't see the particular image, it didn't see any example from these categories. So how can it generate such a beautiful prediction? Now, from the theory, we can at least understand. We suspect that what's going on is that the geometry of the held-out categories were processed in such a way that now the signal increases, etc., etc. So we are asking whether this performance is really consistent with the theory. You see, the theory says, well, these are ellipsoid, participation ratio, and all this stuff. And the answer is yes. So here's the example. So this is the bonobo new category. No, I'm sorry. This is the reference new category, and this is examples, and these are pairs, so there's always pairs. So this is one of the pairs, and this is the distribution of the other pairs. And now we're putting them alongside our SNR prediction here and here, and it beautifully fits our SNR prediction. So the geometric features predicted by your expression really are predictive of the performance in few-shot learning of the real data. Okay? It's surprisingly so, because these are naive, relatively naive measures. More examples. Okay, I don't have time for that. Okay, I want to show you, because I have only a few minutes, I want to show you zero-shot learning. So what is zero-shot learning? I don't show any examples. And I'm only showing you test image. And I'm asking, is it Numbat or Kauti? Well, come on, you didn't show me any example. How can I know? We use language, okay? So what is zero-shot learning is there is no data about the new classes from vision, but we have a linguistic descriptor. So in ImageNet, luckily enough, all the classes trained or held out are coming with a linguistic annotation. So now we use this linguistic annotation to infer what will be, what is this? Is this similar to this or similar to this? So zero-shot learning, there is no visual information. Okay, so how are we going to do it? How are we going to use language to infer about vision? Okay, the way we do it is the following. We take a word embedding, a language embedding, word embedding scheme, whatever, one of the popular ones. So this is like a population distributed representation of words or of words, okay? And what we do is the following. We take the trained images, 1,000 categories, which were trained by the network, by the visual network. We compute their centroids in the feature layer. So we have 1,000 vectors, each one represent a category in the visual feature space. And we look at the 1,000 vectors representing them in the language space. So we have 1,000 vectors and 1,000 vectors for each category. For each trained category, we have the visual representation and we have the language representation. And then we ask, is there a linear map between them? So find the best linear matching between this language representation and visual representation. Once we find the mapping, we freeze the mapping and we show new categories in the language. So then we say, let's use the mapping to predict vectors in the feature space of the vision, and then use those to make a zero-shot learning. And surprisingly, if you do this, surprisingly you find again very high accuracy. In this particular case, 93% of error. And again, we are using similar argument about geometry in the zero-shot learning, and you see how the predictions about the geometry in the zero-shot learning fits nicely with the distribution of errors, not only the average error, but the distribution of errors in zero-shot learning. So this is, I think, a remarkable empirical fact that two things. First of all, heavily trained convolutional networks generate good feature representation, not only for the trained categories, but for generic object category, number one. And number two, that there is an alignment in the language of Jan LeCun, an impressive alignment between two modes of representation of the same concept: language representation and visual representation. Without any training, we just take this. Furthermore, which I don't have to show here, this Ben has done this type of exercise also on self-supervised training, where you don't use any labels in the training, and find that the similar representation of generic object representations appear also in the self-supervised learning. And finally, the last thing which I want to show you, and there's 2 more minutes, is about extending this to something which looks like an completely unrelated, on the first impression, is abstract reasoning. So basically the philosophy, if you can see that from my first lecture, is we start from low-level vision, retina, photoreceptors, ganglion cells, V1, etc. Now we discussed object representations in feature layers of visual systems and so on. Now what about reasoning? What about more abstract computations? Okay, so this work is done by a student at Harvard, Chen Sheng, with Gabriel Kreiman, and I just want to show briefly what is the type of reasoning problem is. So there's a famous reasoning task which is called Raven, or Raven progressive matrices, which is used heavily in cognitive science and in machine vision, which is basically you're shown this type of 9x9 object or images, and there is an underlying rule, and you have to predict what is missing here on the basis, you have to infer the rule and then to predict what is missing here. Okay? So for instance, here you can say, well, there are 3 different objects, so it will be a square here, but they have the same color or the same shade, so it will be this, and so on and so forth. So this is a very common task. Now the question is, you train a network on examples from such abstract rules, and you test the generalization on different instances of these rules. And typically the performance is fine, depending on which network you use. But now it's a harder challenge is you train the network on a subset of rules, and you want to see if the network can reason, the trained network, on a new rule. So for instance, you do a progression on colors, and you want to test on progression on shapes or on numbers. So the network has never seen examples of those. So reasoning for an inference on new rules. Okay, so what is the relation to our work? So here it is a simplified experiment on this. So remember, so what is done here is you are presented with 8 candidates of filling this in, and you have to decide which one is the correct one. So we are doing a simplified version of that. We are shown 1 row, it's enough to infer the rule. And how do we know how to infer the rule is we're showing two candidates. So we're showing this one or this one. And you have to say whether this belongs to this or this belongs to this. So in this, of course, in this case, the shape is uniform, so it should belong to this, okay? So we turn the problem of reasoning into a problem of discrimination on the basis of 2 examples, 2 candidates. You have to infer what is the more relevant rule, this one or this one. Okay, so you can think about this now as kind of one-shot learning. If you think about all instances of a rule as a category of all images, of all rows that satisfy this rule. And this, in that case, will be just classifying a new point on the basis of one-shot learning, basically. Because there is an underlying rule. We don't tell what the rule is, but you have to infer whether this fits this or fits this rule. So you can turn this into one-shot learning, and then the problem of inferring new rules will be a problem of held-out. So it's one-shot learning of new categories, new abstract reasons. So you can turn the whole geometry into this problem of reasoning, inferring abstract rules from data about subset of rules. So this is the extension. Rather than thinking about discriminating new objects on the basis of set of objects, here you have to infer new abstract rules on the basis of having been trained on a subset of the rules. Okay, so what Shane has done is used convolutional networks for this and transformer, and basically generate a relational representation, kind of feature layer representation for each one of this row. So each row has a representation. So now you basically you say, okay, so now I have two examples from a new rule. I have my test point, which is this. If this belongs to this, if this is closer to this, then this is the rule. If this is closer to this is the rule. And does cross entropy loss and finds very nice performance overall. But more surprising is that if you use the same formula here, using the geometry in the feature layer of this object, you find a very nice fit to the prediction from this one-shot learning. So this is where we are. We are trying to use geometric measures of manifolds to understand what controls reasoning. The lower level, the simplest reasoning will be identifying or discriminate between objects. Objects are really visual categories. The next thing what we showed was using language and relation between language and vision representations to inform the discrimination of new objects. And the last one was actually using more abstract categories as organizing manifolds and trying to understand what controls the ability to reason on them. So we can see how this, in my mind, should be going on with new ideas and new mathematical tools, including statistical mechanics, to probe more complex cognitive functions in artificial networks and hopefully also in the brain. Thank you.